Okay, so our next talk will be on high performance deep learning and machine learning work that we do in our lab. So this work is led by Dr. Aamir Shafi. So unfortunately, he could not be here in person due to technical issues. So Aamir is a research scientist at the Ohio State, very nice person, a fantastic person to work with. I have been blessed with the opportunity to work with him over the last several years. So he did his postdoc at MIT. He was a visiting scholar there, working with very, very famous people. And joining Aamir today will be Nawras. He's a PhD student working in the deep learning project. And they will be talking about what we have been doing to enable high performance machine as well as deep learning with MVAPICH2. So without further ado, let me hand over the stage to Aamir and Nawras, and let's welcome the speakers.
Thank you, Hari. So you're able to hear me. Are you able to hear me, Hari? Just needed a confirmation. So can you guys hear me? Hello.
Okay, Aamir, can you hear us?
Yes, Nawras, I can hear you. Can you hear me? Hello, can you hear me?
Yes, we can hear you.
Nawras, can you hear me?
Yes, we can hear you. Can you hear us?
Okay, excellent. So I'll get started. Yes, I can hear you. Yes.
Okay, great.
Okay. So thank you, everybody. Thank you, Hari, for the kind introduction. So today we'll be talking about our high performance deep learning project, and we'll just share the latest progress on this particular project. So Nawras Alnaasan, is my colleague who will be co-presenting. So here is the outline. First, in the first part of the talk, I will outline the developments in the area of machine learning, and then in the second part, Nawras will present what we have been, doing in the context of deep learning. So I think I don't need to, put a lot of emphasis on this, but in our generation, perhaps deep learning has become one of the most important workloads, and there are different types of DNNs like convolutional neural networks, recurrent neural networks, and more recently these generative AI models. They have actually been very useful, and people are trying to train large and large models, and this has sort of become an HPC problem as well, and this is where our group and MVAPICH2 comes in. So this is just a brief history in the development of ML and DL. So while some of the key concepts have been around for a very long time, but in the 70s and 80s, we were stuck by this the so-called dark age, which was the AI winter. The intelligent networks at the time were not even able to solve the ZOR problem. But then with the introduction of multi-layered perceptrons and backpropagation, we were able to solve that problem, but that turned out to be really compute intensive. So, everything changed in 2012 with the introduction of AlexNet, when AlexNet was, able to perform very highly in the ImageNet challenge. And since then, we have seen, a dramatic rise in the adoption of neural networks, and more recently, models like GPT, ChatGPT, and other language models, they have actually been very useful, and it's fair to say that it's one of the most revolutionary ideas of perhaps our age. So in the next section of the talk, I'll be talking about machine learning. So we'll start off with the the basic k-means algorithm, but before that, there are mainly three types of machine learning. I mean, if we have to segregate by areas, supervised learning, where we basically teach our model by giving it examples, unsupervised learning, where we are given kind of an input and then asked to, let's say, categorize the input. And then, another area is reinforcement learning, where a piece of the software basically learns from the environments and make intelligent decisions. So in the context of parallel and distributed execution, so the common wisdom has been that the machine learning algorithms or applications, they are not very compute intensive. For that reason, the most widely adopted machine learning library, which is scikit-learn, it actually doesn't even have the support for GPUs. But it's possible to run it on in a parallel and distributed way. So there are softwares available like JobLib. It's possible to run it in a multi-threaded and multi-process environments. And then there are also some other libraries coming up like SGBoost that rely on gradient boosting algorithms, and they have support for parallelism through third-party softwares like Dask, Ray, AWS Yarn, and others. But in this context, one of the libraries, machine learning libraries that has support for GPUs, which has obviously become important now with the emergence of large data sets, is QML from NVIDIA. And this particular library supports execution of multi-nodes using Dask and using NVIDIA's Nickel communication library. So here is a high-level overview of the k-means algorithm. So we are basically given a set of input elements, and then we would divide these into however number of processing elements are available to us. And after that, each GPU will perform some local computation. So for example, in this case, for a typical k-means, we will basically, for each GPU will calculate the mean of the local elements. And once we have the mean of the local elements, we'll basically perform an OR-reduce operation to basically come up with the global minimum. So basically, the compute intensive part in this k-means algorithm, or the communication intensive part here, is essentially this OR-reduce algorithm, and this is where essentially MVAPICH2 also comes in. So next, I'll talk about some of the solutions that we have developed. So this is an overview of the QML library. So this is coming from the NVIDIA Rapids project that aims to build end-to-end data science pipelines on the GPU. QML is one of the important part, and it's fair to say that this is the GPU counterpart of scikit-learn, and this supports the execution of ML workloads on multi-node, multi-GPU systems. And as I've mentioned earlier, so most of the other ML libraries like scikit-learn and Apache Spark MLlib, they only support CPU execution of ML algorithms. So here are some of the main components of the QML library. So if you look at the top figure on the right-hand side, at the top we have the Python layer. So the developers of QML they have put in significant effort on making sure that the API is still the same as scikit-learn. And then they have implemented a few algorithms like linear regression, logistic regression, but then there are a bunch of primitives available. So the idea here is that, if your favorite machine learning algorithm is not available in QML, you could still make use of these primitives and implement these algorithms yourself. So if we look at the architecture figure, which is at the bottom right, we basically see from the top, we have the Python layer where we have Dask, and this interacts with the core CUDA C and C++ layer. And essentially for parallelization, Dask is being used, UCX is also used, but for collective communication library, Nickel is used in the QML software. And I think the core ML algorithms are implemented in C++ layer. I mean, the block here that you see as QML algorithms, and also there is support for QML primitives that can be used to do optimized linear algebra operations on a GPU. So what we have done as part of the QMLs, as part of our software called MPA for QML, is that we have added support for MVAPICH2 GDR in the QML software stack, and we have been able to do that. In addition to using Nickel, it's now possible to use MVAPICH2 GDR for collective communication operations. And obviously, since this is a Python-based software stack, so we had to rely on the MPF or Py software to be able to essentially do that. And the most recent release of this software is 0.4, which is our essentially, MPF-driven ML training. And this basically supports, MVAPICH2 GDR, and it also supports a bunch of ML algorithms that have been that are available in QML 22.2. So this is basically February 22 release of QML. And so it's now possible through command line switches to switch from nickel to using MVAPICH2 GDR and basically make use of the software. And this particular software is available from our HighDL website, and you can go and download this and give it a try. So this last slide on QML is the performance comparison. So for example, if we just focus on the k-means algorithm here, so on the x-axis we have the number of GPUs going from 1 GPU to 16 GPU, and then we have two bars here, the green bar and the blue bar. So the blue bar here is, when we have used MVAPICH2 GDR for parallelization, and the green bar is when we are using nickel for communication. So, and as you can see on 16 processors, so for almost all the different algorithms, we are seeing, performance benefits, and for the k-means one, approximately 1.6x speed up was witnessed. And this evaluation was done on the Expense GPU system that is equipped with NVIDIA V100 GPU, and the other details are also available here. So with this, I will now hand it over to my colleague Nawras to continue, please.
Okay, great. So next we're going to talk about deep learning. So we all know that deep learning is getting very, very popular these days. But deep learning applications are very compute intensive. So the question is, how can we use MPI and HPC resources to be able to do execute deep learning applications more quickly? So first, let's cover some basic concept in deep learning, deep neural networks. So this figure here is showing a 3-layer deep neural network, DNN. And to train a deep neural network, the training process consists of 2 phases mainly, the forward pass and the backward pass. And in the forward pass, we basically propagate the input. So we have here X is the input, and then we propagate it by basically multiplying the activations with the weights. And then at the output layer, we get the prediction. Based on that prediction, we calculate the error. We take that error, we propagate it back during the backward pass to basically calculate the error and update our network. So this is the main computation that is done in deep learning applications. One very important concept is learning rate. Learning rate is a hyperparameter that is optimized like before the training. And basically, if you pick a learning rate that is too low, your learning might take forever because you're taking very small steps to reach your minimum point, minimum error, basically. And if you pick a learning rate that is too high, you might oscillate between basically the 2 sides of your learning curve, never reaching or converging to the minimum. So picking the right learning rate will guarantee that you smoothly converge to the minimum. And this is very important in distributed training because you need to optimize this when you run on different number of machines. So another important concept is the batch size. There are many ways to do DNN training, choosing different batch sizes. So one way is the batch gradient descent. And in this way, we basically take the entire data set, we do the forward and backward pass, we calculate the gradients, and then we perform the update. This is not the best way to perform DNN training because you're basically relying on too much information to do your update. Also, training on the entire data set might take too long. Another way is called stochastic gradient descent, where you randomly select a sample from the data set, you perform the forward and backward pass, and then you update the network. This is also not the best way because first, you are relying on too little information to update your network. And the second thing, you're only processing one sample at a time. So you're wasting compute resources because you can process many samples at the same time and like do more work in parallel. So another method is called mini batch gradient descent, which combines both of these techniques. You can determine a batch size, so basically a subset of your data set. Let's say like 64, 128, 256 samples that you perform the forward and backward pass on, and then you update your network based on the gradients that you calculate. And finding the optimal batch size and learning rate will yield the best and fastest learning. So these are things to take into consideration when you do distributed deep learning. So why do we need distributed deep learning? Basically, deep learning models are getting larger and deeper. And like many recent studies showed that when your model is larger, you'll get better generalization, you'll get better accuracy, and you can train on larger data and more complex data. So to do that, you need more compute resources. And if you do it on a single GPU, that might take forever, like weeks or months to train a single network. So one way to do it faster is to use multi-GPU training. That is, if you have one machine with many GPUs in it, you can distribute your workload or like process the training in parallel. But even better, if you have an HPC, okay. We're back on. Yeah, so if you have like an HPC system with many machines on it, you can do multi-node training or distributed multi-node training, where you can use many machines and each machine will have many GPUs, and ideally you'll scale your learning and it will finish much faster. So how can we do distributed training? How can we parallelize the training process of a deep learning application? There are many ways. Data parallelism perhaps is the most famous one, where you take your model, you replicate it on the different machines, and then you feed it different data samples. Another way is called model parallelism, where you split the model itself across multiple machines. And finally, hybrid is a combination of both, where you do model and the data parallelism. So this is how data parallelism works. You first have your data, so the batch, and then you split the batch across different GPUs. So in this example, we have 4 GPUs. And as you can see, each GPU has its own parameters. So it stores its own local parameter of the deep learning model that we are training. And then based on the samples that this GPU gets, we do the forward and backward pass, okay? And then once we do the backward pass, we end up with local gradients. So now each GPU has its own local gradients. And to sync up all of these local gradients, we perform an MPI operation that is called all reduce. And basically, this will aggregate all the local gradients. We'll end up with global gradients on all the GPUs. So those global gradients are the same. And based on them, we're going to update our model. And this is just one iteration of many. So this is done like on a batch level. So let's say the batch size is 32. Then for every 32 samples, we do this iteration. So as you can see, for like large data sets, we're going to end up calling all reduce many, many times. Okay. So now let's look at some of the DL solutions, the distributed DL solutions that use MPI. So this is like this is the HighDL stack, high performance deep learning stack using the MVAPICH2 library. So at the top level, we have the MLDL application, and then under it, we have the deep learning framework like TensorFlow, PyTorch, MXNet, and underneath it, we have a middleware that is responsible for implementing the distributed training algorithm like Horvath, Torch Distributed, and Deep Speed. And then beneath, we have the communication backend like the MVAPICH library, which optimizes the collective operations. So how do we install this HighDL stack? It's very simple. It's just a one-line command. Of course, we need to export all the variables for MVAPICH before, and then we execute this command to install Horvath. Now let's look at a live demo. So this is on a V100 system. So we have many nodes with a V100 GPUs. And then we're gonna run a PyTorch benchmark on one GPU and see the performance. So this is using just a single GPU. The model that we are training is ResNet 50. The batch size is 64, so we're processing 64 samples at a time. And then this is running for 5 iterations, and we're taking the average. And then we can see that the throughput is around 334 images per second. So this is how many images we can process per second. And then now we're going to run it on 2 GPUs. So 2 nodes, each node with 1 GPU. And you can see the command is slightly different here. We're using MPI run. And we're saying, OK, run this on GPU 8 and GPU 9 with these with this configuration. We're doing the same benchmark, ResNet 50, but now it's on 2 GPUs. And then we can see that the combined performance of the 2 GPUs is around 624 images per second. So this is pretty good. It's almost linear, around 1.9x on the 2 GPUs. There is a slight overhead for setting up the distributed training. But like if we scale beyond that, we see consistent performance. So this is the HighDL software stack release version 1. If you're interested, you can find more details in this link. We released this earlier this year. And basically, we offer optimized MPI controller for deep learning workloads. We have efficient large message collective implementations. So like the OREDUCE or other collectives like AllGather and All2All that are used in model parallelism. We support fork safety, which is needed for many deep learning applications, and it's compatible with different hardware and software configurations. So these 2 figures are comparing nickel on the NVIDIA A100 GPUs and RICL on the MI100 GPUs. And we can see for NVIDIA, we are doing slightly better than nickel with MVAPICH 2 GDR. And with AMD GPUs, it's around 1.47x improvement over RICL. Okay, so now let's look at, so in these numbers, we've scaled to 24 GPUs. Let's see if we can like scale beyond that. Like, what is the limit? Is there a limit? Can we expect this performance on thousands of GPUs? And the answer is yes. So this is training ResNet 50 using TensorFlow on 1500 V100 GPUs. So this is on the ImageNet dataset, which is around 1,200,000 images. And we were able to train the entire network in 4.5 minutes. So on an average of like 3 seconds per epoch. So the scaling is almost linear up to 1500 GPUs. It's also the same on the CPUs. So you can also get pretty good performance if you use the CPUs to do DNN training. And in here on 2K nodes, we were able to train the entire network in 7 minutes. Okay, so this is a more specific solution. We found out that basically for smaller DNN models, you might be underutilizing your GPU. So why not exploit data parallelism even more? Let's place more model replicas on the same GPUs. So previously we're placing one model replica per GPU. Now let's place even more. And by doing that, we're seeing up to 30% and 62% improvement based on the DNN model. Okay, so that is for data parallelism. Now let's look at some solutions for model parallelism. So model parallelism is needed when the size of the model is too big to fit in the memory of a single GPU. But there are also other cases where model parallelism is needed. So for instance, if your image is too big, right? So like usually deep learning applications use 32 by 32 or 256 by 256 images to do the training, which is like quite small and it fits in the memory of the GPU. But like, what if you have a 100K by 100K pixels image? This is too big to fit in the GPU. One solution is to split the image, right, into tiles and do the training on the tiles. But this way you'll lose the structural information. So this is an example from digital pathology where you have like a slide image. And if you break it down, you'll lose the context. So you need to train it on the entire image. So one way to address this is to use model parallelism. And you can combine model parallelism with data parallelism to reduce the training time. So the like basic training with model parallelism is around 7.2 hours. And you can reduce it to 27 minutes on 32 nodes and 128 GPUs. Okay, so like how can you use this model parallelism solution? We have an upcoming release called MPI4DL version 0.5. And MPI4DL is basically a distributed and accelerated training framework for very high resolution images. So it integrates many different parallelism techniques like spatial, layer, and pipeline parallelism, and also combinations of these parallelism techniques. So you can bring your own images that are very large, and then you cannot train it with like simple PyTorch or TensorFlow, but with this framework, with this package MPI4DL, you can train any size image. So this is an example of training AmoebaNet with an image size of 1K by 1K. Blue is like vanilla pipeline parallelism, and then orange is a spatial plus pipeline, which is implemented in MPI4DL. And we can see the improvement in performance. This is the throughput. Top is 1K by 1K, and bottom is 2K by 2K. Okay. So to conclude this, there is an exponential growth in machine learning and deep learning frameworks. And with that, there are a lot of issues and challenges and opportunities to design better solutions to perform distributed training and accelerate the training. We presented some cases that showed like complex problems and how to solve them, which with HPC technologies and MPI. And most importantly, this is still an evolving field, and it needs a lot of collaborative efforts to achieve the full potential. So yeah, please, I mean, if you have any questions or if you'd like to discuss this further, I'd be happy to talk with you, and thank you very much.
Oh, thank you for the talking. I'm wondering about data set in the experiment. So it is synthetic data set or ImageNet or something like that?
So that depends on the experiment. If the objective of the experiment is to just measure the throughput, then it's a synthetic data set. But if it's like accuracy is also important, then we use real data sets like the ImageNet data set. So for the demo I showed, it's a synthetic data set because we're only interested in the throughput. But for the training the entire network on 90 epochs, that was on the ImageNet data set.
Thank you.
Sure.
Any other questions? So if not, let's thank